Hello class, this is our chapter 3 review and we are going to summarize what we've learned about second order homogeneous differential equations with constant coefficients. What this means is that instead of a px and a qx, we just have a p and q. These are constants. Now this is, I would consider, the most important part of chapter 3. So if you have to if you can only master one part of this chapter, make sure you understand this part fully because everything else sort of flows into it. And another thing I want to suggest is that for the test especially, that you do not skip steps. Like write down every step, every substitution. It doesn't take that long, and I know that in the homeworks you were allowed to sort of like skip a few steps and rush through the problem a little bit. But for the test, taking it slowly will help you avoid mistakes. And if you do mess up, make an error somewhere, if I see you making the steps correctly, I can more easily give you partial credit. So I would suggest that you actually make every substitution and don't take any shortcuts when solving these problems. The key trick of this type of problem is, of course, the substitution y equals ERX. We make the substitution, and please write down all the derivatives that you use to substitute it correctly. In this case, we have a second order equation, so we have to take two derivatives, and by a simple chain rule, we have that y prime is equal to r ERX, and y double prime is equal to r squared ERX. Substituting back into the original equation, we have then that r squared ERX plus p r ERX plus q ERX is equal to 0. And we can make the appropriate factorization, just factor out the ERX term. And we reduce our problem to this form, r squared plus pr plus q times this ERX term. Now, the equation is asking for something to be 0, and we know that exponential functions are never 0, so we can cancel it out, and the problem simply becomes to solve this quadratic equation. Now, I know that you are all pretty familiar with the shortcut. You can just like go from y double prime to r squared, from y prime to r, and from y to constant in that way. And I've let you do this in the homework and in class. However, for the exam, I would ask you to write down every step we've done so far, to actually write down the substitution. It will make your life and my life a lot easier when you take the exam. So please, please don't take shortcuts in the tests. So anyway, you have this quadratic equation, and you solve it. And the next step is to understand how the roots correspond to solutions of the differential equation. If you have r equals a, where a is a real number, you can just substitute it back into your original substitution, y equals ERX, to obtain y equals EAX. So this will be one solution of your differential equation. And if r equals plus or minus ib, where I is the square root of -1, and also note that the plus ib and minus ib always come in pairs. That's because of how the quadratic equation is written. We can plug in the r to get y equals e plus minus ib. This solution actually works if you plug it in to the differential equation. That's fine. However, we typically want to avoid complex solutions, so we have to try to rewrite it somehow. And the way we rewrite it is using this Euler's formula. ei theta is equal to cosine theta plus I sine theta. So we know that eibx is equal to cosine bx plus or minus I sine bx. And again, these are perfectly fine solutions. However, since we prefer real solutions, you can just take the real and imaginary part of the previous solution to get y1 equals cosine bx and y2 equals sine bx. And this is what we'll use. So remember, we only get cosine and sine functions if we have imaginary roots for the characteristic polynomial. If we have a root r equals a plus or minus ib, then we have a combination root too. We write down, we substitute back in the r, and we get y equals e raised to the a plus or minus ib x. And this can be written down as eax times e plus or minus ibx, based on how exponentials distribute. And this basically gives us the combination of the previous two cases. And y1 equals eax cosine bx, y2 equals eax sine bx. And this is what solutions the roots correspond to. And you can use the principal of superposition to find the general solution. Just a few examples. So if, for instance, r is equal to 1 and 2, we know that y1 is equal to ex and y2 is equal to e2x. So the general solution is going to just be a linear combination of those two. So you have y equals c1ex plus c2e2x, and so on with all the other solutions. So the roots correspond to the solutions, and you can use the principal of superposition to get the general solution in this way. But remember that for the general solution, we need your different solutions to be linearly independent, and this poses a problem when we have repeated roots. Let's say, for example, our polynomial has the root r equals 3 repeated 3 times. What this means is that rather than writing down y1 equals e3x 3 times, we have to in fact multiply each of the solutions by x to get 3 linearly independent solutions. Because y1 equals e3x, y2 equals e3x, y3 equals e3x will not be linearly independent. So these will be our 3 linearly independent solutions. And as a final note, remember that these principles work in reverse as well. If your differential equation has a solution y equals ax, it means your characteristic polynomial has a root a, and therefore r minus a is a factor of that polynomial. And also if y equals cosine bx is a solution to your differential equation, r equals ib is a root, and r plus ib, r minus ib are both factors of the characteristic polynomial. And you can sometimes use this information to solve more complicated problems.